Okay. Next speaker, Professor Vasyl Fedorchuk. Title of the talking on symmetry reduction and some classes of invariant solutions of the 1 plus 3 dimensional homogeneous Monge-Ampere equation. Please.
First of all, I am grateful to the organizers for the information about the conference and the possibility to give me this talk. Now some words about application of the Monge-Ampere equation. It is known that the solutions of many problems of geometry, theoretical physics, one-dimensional gas dynamics, meteorology and oceanography, etc., has reduced to the investigation of the Monge-Ampere equations in the spaces of different dimensions and different types. The details on this theme can be found in. I concentrate my attention on the application of the Monge-Ampere equations in geometry. First of all, we see sophusly next цицеється, namely цицеється surfaces in 1977. Next problem geometry deal with Huygens and will solved in 1954. Next generalization of this problem with concern with existence hypersurfaces, convex hypersurfaces in 3 and 4 dimensions. This problem was solved by Calabi 1958. Next problem geometry, which reduced to the investigation of the Monge-Ampere equations, is the so-called many-dimensional Minkowski problem, which was solved by Pogorelov in 1971 and generalized and repeat the same solutions by Cheng and Yao in 1976. Next geometric problem, which reduced to the investigation of the Monge-Ampere equation, deals with the Calabi conjecture, which can be solved by Yao in 1978. And in theoretical physics, Monge-Ampere equations have many applications, namely connected with so-called Calabi-Yau manifolds The details can be found in Jaunedis 210. Next problem connected with has dynamic and etc. Here we see a lot of scientists which worked with and work now with Monge-Ampere equation in the spaces of different dimension and different types. As we see, here these scientists from different country and different work with Monge-Ampere equation in different time. Symmetry reduction is one of the most powerful tools to investigate partial differential equation with non-trivial symmetry groups. In particular, for this purpose, we can use a classical Lie-Ovsyannikov approach which allow us to make symmetry reduction and construction invariant solutions of the equation with non-trivial symmetry groups. Here is the picture Marius Sophus Lie, main contributor and the founder of this approach. Next picture, Ovsyannikov and Peter Olver and many another scientists. In many cases, invariant solutions of partial differential equations are non-singular manifold which invariant with respect to the non-conjugate subgroups of the symmetry groups of the equation under consideration. The details can be found in Lie, Ovsyannikov, Grundland, Harnett, Winternitz, Olver, and etc. According to the classical group analysis, classification of symmetry reduction and invariant solutions should be performed with respect to the rank corresponding non-conjugate subalgebras of the Lie algebras of the symmetry group of the equation under investigation. The details can be found in the following works. And now we have continuation scientist. However, it turns out that many scientists have obtained different type of the reduced equation by using anxieties or non-singular manifolds invariant with respect to non-conjugate subalgebras of the same rank. This it was pointed first of all by Grundland, Harnett, Winternitz in 1984, and the same situation we see in the scientific works of another authors. No, as we see, we obtain scientific works different year and from scientists of different country. No, the result obtained cannot be explained using only the rank non-conjugate subalgebras of the Lie algebras of the symmetry groups of the considered equation. To classify the symmetry reduction and invariant solutions, the equation with non-trivial symmetry group, we have suggested to use the structural property of the low-dimensional non-conjugate subalgebras of the Lie algebras of the symmetry groups of the equation under investigation. Now, I have described that in order to realize this suggestion, we have to solve pure algebraic problem which consists in classifying of Lie algebras, finite dimensional Lie algebras according to the type. If we use non-conjugate subalgebras of the Lie algebra of the symmetry group, we first of all can classify these non-conjugate subalgebras into isomorphic classes. Now some words about the symmetry of the Monge-Ampere equation in the spaces of different dimension and different types. As we see, first work is connected is work of Sophus Lie, 1885, and he investigated the symmetry property of the Monge-Ampere equation, so-called one-dimensional. Now, symmetry property of the two-dimensional Monge-Ampere equation, homogeneous, have been studied by Chupachin and Ibragimov. In 1983, Fuščić and Serov have investigated symmetry property of the many-dimensional Monge-Ampere equation of the following form. In homogeneous Monge-Ampere equation, U mini is a second derivative of the function u with respect to x mi, x ni. U mi is first order derivation, mi ni equal from 0 to n. The results, the same results, Fuščić and the same results can be found in the monography Fuščić, Stelling, and Serov. Symmetry property of the many-dimensional Monge-Ampere equation of the following form. In homogeneous Monge-Ampere equation, but right-hand side does not depend on first derivative function u with respect to x. This result was obtained by Udrishte and Bila. And the symmetry property Monge-Ampere Tsitseitsa surfaces equation have been studied Udrishte and Bila in 1999. In my report, I plan to present some result concerning the symmetry reduction of the homogeneous Monge-Ampere equation in the space μ13 multiple IU, where μ13 is 1 plus 3-dimensional Minkowski space. IU is the real number axis of the dependent variable U. Let us consider the Monge-Ampere equation of the form. From the work Fuščić and Serov, it follows that this equation is invariant with respect to the generalized Poincare group P14. In order to classify non-conjugate subalgebras of the Lie algebra of the group P14 into classes of isomorphic subalgebras, and the result was obtained in this year. The Lie algebra of the group P14 contains the following type subalgebras. We have two types, so-called decomposable subalgebras and 9 types of the so-called indecomposable subalgebras. No, we obtain the following type of the reduced equation when we used 3-dimensional non-conjugate subalgebras of the Lie algebra of the group P14. We obtain 4 types: identity, linear ordinary differential equation, nonlinear ordinary differential equation, and partial differential equation. From the result obtained, it follows that the reductions to identity can be obtained using subalgebras only of the only 6 following types. Below we present some example of the reduction of the Monge-Ampere equation to identity. If we consider subalgebras as example, one subalgebras of the type 3A1, we see basis elements of subalgebras, ansatz, and solution of the Monge-Ampere equation with an arbitrary smooth function phi. If we consider the next type of 3-dimensional subalgebras, we obtain for basis elements of the Lie algebra ansatz and solutions of the Monge-Ampere equation of the following form, where phi is an arbitrary smooth function. Now, if we consider subalgebras of the type R31, so-called indecomposable subalgebras, we can construct the ansatz of the following form, and we obtain the solution of the Monge-Ampere equation, where phi is an arbitrary smooth function. Thank you for your attention.
Thank you very much for talking, Professor Vasyl Fedorchuk. Any questions, comments? No. Again, thank you very much.
Thank you again.
10 minutes break.